Hello, everyone, and welcome to today's webinar, Managing Secrets with Chef and HashiCorp Vault. My name is Jamie Bright, and I work on the marketing team here at Chef. And I'm pleased to introduce today's speakers, Seth Fargo and JJ Asgar. Seth is the Director of Technical Advocacy at HashiCorp, and JJ is a Senior Partner Engineer here at Chef. But before we get started, I have a couple of housekeeping items to cover quickly. A recording of this webinar will be available on demand after the live session, accessible through the same link you're using now. We'd also love to hear from you during today's presentation. Seth and JJ will be answering questions at the end of the session, so please feel free to send those along at any time using the Ask a Question tab in your viewer. Then after the live presentation, we'll be including links to additional resources for this topic in the Attachments tab of your viewer, so you can check those out later when you're reviewing the recording. For those of you that are just joining, welcome to today's presentation, Managing Secrets with Chef and HashiCorp Vault. Let's go ahead and get started. Seth, why don't you kick us off by telling our audience a little bit more about yourself and what we'll be covering here today.
Great, thanks Jamie. Today we're going to be talking about how to manage secrets using Chef and HashiCorp's Vault. But before we get started, I'd like to take a step back and talk about what is a secret. Then we're going to talk about existing solutions for secret management using Chef, and then we'll talk about Vault's architecture and design, and then we'll talk about how the two integrate together. And then we have an extra special surprise for you at the end of the webinar, so please be sure to stick around to the end. So what is a secret? Well, a secret is anything which, if acquired by an unauthorized party, could cause political, financial, or reputation harm to an organization or a person. So when we think about secrets, we generally think about things like passwords or social security numbers or credit card numbers, and it's very easy for us to think, oh, those are secret. But when we start asking questions about things like email addresses and phone numbers and home addresses, are those necessarily secret? And sometimes in those situations, it really depends. For example, the phone number of the President of the United States is more secret than my phone number. And the address of, a foreign dignitary is more secret than my home address. So in some cases, having a secret is black and white. In other situations, it's really a gray area that depends on the context. And this is where it's important for you and your organization to really understand what data is and is not secret, and therefore how it should be handled. No matter how well you use Chef or how well you use Vault or any secret management solution, there's ultimately an organization decision that has to be made of what do we consider secret, and what do we consider sensitive, and what do we consider personally identifiable information. Along those lines, we have to ask ourselves, for how long is a secret a secret? There's a famous quote that says the only way to keep a secret between three people is to eliminate one of them. And how long after we have created a secret or created a credential does that secret remain secret? We frequently rotate things like login credentials to a server. You might be using something like Active Directory or LDAP, where you can set policies that say users need to change their passwords or rotate their passwords every 30 days or every 7 days, and you enforce password requirements there. On the flip side, when is the last time you changed your wireless password to connect your devices at your home or in your office? Or when's the last time you rotated your SSH key? And the reason that I ask this question and start to get you thinking in this line of questioning is because when we start talking about Vault, you'll notice that Vault architecture is one of a lease-based architecture, meaning secrets have a lifetime, and they're only secret for a certain period of time. And that's going to be crucial when we start talking about Vault architecture. So keep that in the back of your mind of when is the last time you changed your Wi-Fi password, and why haven't you changed it since then? And then the last component I want to talk about, the last thought-provoking question before we jump into some stuff here is, what is your current process for doing a concrete secret acquisition? So I want you to imagine the last time, maybe you're a developer, maybe you're an ops person, but when is the last time you needed to access a database credential for an application in your organization? Meaning you need to get a username and password so a user or an application can access a database. And for smaller companies like startups or small organizations, this might involve, logging into a server, running some commands you found on Stack Overflow, and then, copying the generated credential into a text file, checking that into source control, and, rotating it over time. For a larger company, the process is a bit inverted. You might have to file a JIRA ticket, wait for your DBAs or, the team that manages credentials to get you the credential. That might take a month or 2 months, and then you have the credential delivered to you, securely or insecurely for you to put in your application. And this is important to think about, the two different ways we acquire secrets and the mechanisms for them, because this webinar is actually going to explore a hypothetical scenario that involves that process, which is how do we acquire a database credential and put it into a text file so a fictitious web application can communicate with the database. So I'll say that again, the kind of the gist, the overall theme, the goal we're working towards in this webinar is a hypothetical scenario in which a web application needs a database credential from some type of text file, like a YAML file or a JSON file, so that it can communicate with the database. And we're going to talk about not just the process of getting that, but the technology behind it, and then how the people are involved. So we're going to discuss the people, the process, and the technology. So before we start talking about Vault and secrets management or any of these things, it's really helpful to review some of the techniques which you may already be using. And I'll preface this by saying none of these techniques are bad. They have their own trade-offs, which we'll identify. But you may be already doing these, and this is not meant to say, you're doing it the wrong way. In fact, there's always, more than one way to shave a yak. And whichever way works best for you is always the best solution. So if we take a look on this instance that I provisioned here, I have a few different chef recipes that I've built in advance for the sake of time. The first technique I want to talk about for using secrets with Chef is probably the most basic and easiest to understand, which is to put your secret directly in the recipe. So let's take a look at that. Here I have a chef recipe using a file resource, and it's writing out a file to tempdatabase.yaml, which is just our configuration file. And then I'm using inline content. This could have been a template resource. You could have used a remote file resource. There's a number of techniques to do this. The important part is that I'm just putting the credentials directly into the file resource. So we're hard coding the username and password for this particular application to connect to the database. And we would run this using, if this was a cookbook, we would run this using the Chef server. I'm going to use the Chef client in local mode for this webinar, but these things apply to Chef Solo, Chef client, Chef Zero, the whole 9 yards. So let's go ahead and execute that. And we'll see here, I'm running the latest version of Chef client. It's going to go ahead and pull that cookbook down. And you can see here from the diff that it did in fact create that file. It wrote to tempdatabase.yaml, it updated the contents, and down here in the diff that I've highlighted, you can see that we have a username and password. And our application can consume that particular file, and it is completely unaware of secret management. It doesn't have to worry about how to control it. It just reads this file from disk, and that's where it gets the data from. So let's talk about some of the problems and trade-offs. Well, the obvious advantage to this approach is that it requires almost no knowledge of secret management. We can put our secrets directly in the recipes. We don't have to think about them, but that comes with a trade-off. Most importantly, that the credentials are visible to anyone with access to the Chef repository. So even an intern or a new employee who comes along and wants to change a completely different cookbook has access to these secrets. Additionally, we don't have any separations of concerns. So an attacker only needs to compromise one system, in this case, the Chef repository or this particular cookbook, and he or she has access to the entire system. We want to make it a little bit more difficult, increasing the number of systems that must be compromised in order to have a data breach. Another technique for storing sensitive information is using things like node attributes. I'm using local mode here, so I'm using Chef client -Z or Chef Zero. So I faked it a little bit because I didn't stand up a Chef server, but these node attributes themselves would work on a Chef server as well. So here I have that same file resource. Again, I'm writing out the content in plain text, but you'll notice that the content itself, the username and the password, are using that Ruby interpolation with the PostgreSQL username and PostgreSQL password. And those are interpolated right there in the text file. The advantage here, when we compare that to the previous directly in the recipe, is that we're no longer storing the plain text files here. And these node attributes could be stored on the Chef server. They can be wrapped in ACLs, which is a substitution for encryption, but we can wrap them in ACLs so that an attacker has to compromise multiple systems at the same time. So let's go ahead and run Chef. So we'll go ahead and run the Chef client here. And you can see here we have the database.yaml file, the same file we ran before, and you can see that it updated the username and password to pull from these node attributes. So the attribute was previously named direct user, it's now adder user, and the password is adder secret. So this is the first two techniques. Again, the first was putting it directly in the recipe. The second technique is using node attributes. The third technique, which many of you are probably familiar with, and it's probably one of the techniques you're using, are data bags, or specifically encrypted data bags. So let's take a look at that. So in advance, I've gone ahead and created an encrypted data bag here using the knife data bag command and subcommands. I have a username and a password. These are stored in the Chef repo, but they're encrypted with a shared symmetric secret. So you can see that there are no plain text values here in this particular JSON file. So I'll go ahead and quit this out, and then let's take a look at the recipe itself. So the recipe itself is going to look very similar to the last example with node attributes, except we're pulling at the very top here. You can see we're pulling credentials from a data bag item named PostgreSQL in the data bag named secrets. And then we're just pulling those credentials directly into the raw file contents here. So again, same technique, same file resource. You could be using remote file or template. I'm just showing you as much as possible in one file here. But now we're using a data bag item, and with Chef 12, that data bag item is automatically interpreted as encrypted. So we don't have to do the Chef encrypted data bag item Ruby. We can just use data bag item directly, and it'll decrypt it for us if our encrypted data bag secret is in the right place. So let's go ahead and run the Chef client now. So I'm going to run this recipe called encrypted data bags. And very transparently, it's going to go grab that JSON file, which is encrypted. It'll use the encrypted data bag secret, which I have on this machine. It'll decrypt those values, and then you can see here in the diff that the username and password are now changed. And in fact, if you were to decrypt that JSON data bag I showed earlier, you would find that the username and password were encrypted user and encrypted secret for the username and password. And this is one of the more common patterns that I have seen in the community. So let's talk about some of the advantages. Obviously, it's encrypted. You have to compromise multiple systems because the encrypted data bag secret could be stored offline. It allows you to control which nodes have access to secrets. If you don't distribute the encrypted data bag secret, the nodes can't decrypt the data. It's still possible to check these into source control, so you get all of the benefits of source control management. But some of the problems include a lack of auditing. So it's very unclear. There's not a lot of insight into who is using an encrypted data bag and for why. The secrets are shared across all of the nodes, meaning if a credential is leaked, we don't know which node or which Chef client was responsible for that leak. Additionally, it makes it very challenging to revoke a credential, because if we revoke a database credential, we end up revoking it across all nodes as opposed to a single node, which could cause downtime in our organization. These credentials here have an infinite credential lifetime, meaning this database credential that we've written to the file is valid forever until somebody goes in and manually rotates it, and then we have to make sure that a human comes in and implements the proper process to rotate those credentials and delete the old ones. Which brings me to the final point, and really the biggest problem with this particular strategy is that it requires manual intervention, meaning a human being has to log into the database, right, Postgres, MySQL, MongoDB, They have to run some commands or run a script to generate a user. Then they have to take those generated credentials and put them into some secret system. Regardless of whether you're using encrypted data bags or directly in the recipe, a human being is involved in seeing those credentials. And that's problematic because we can't ever say with 100% certainty if a database credential is leaked or any credential is leaked, who or what is responsible. We lack what is called provenance, which is a finite line of one-to-one relationships between entities in a system. If we see that a particular database credential has been leaked, we can't tie that back to one machine or one user because it's spread across multiple devices. It's kind of the opposite of the pigeonhole principle. And this is really important in an organization that focuses on things like compliance, like PCI compliance and HIPAA compliance, is not only being able to be resilient to attacks and hacks, but also to be able to respond to them in a timely manner. And without that provenance, that one-to-one relationship between entities, it's challenging to do that. One last thing I wanted to point out, one technique that you might be using is a Chef extension written by the fine engineers over at Nordstrom called Chef-Vault. It's important to note that this tool isn't associated with the HashiCorp Vault. It was written in advance. It just happens to use the name Vault. It's a very common name for a secret management solution. Chef-Vault does provide a pure Chef-based implementation for generating per node secrets, but it still shares some of the problems with encrypted data bags, including the lack of auditing, the infinite credential lifetime, and that, most importantly, that requirement for a human to go actually generate a credential. So at best, two people, one human and one machine, know those credentials. So to kind of summarize all of the problems from the previous techniques, we have storing secrets in plain text, which is a bad idea, reliance on ACLs instead of encryption to secure data, lack of auditing and of visibility into secrets and credentials and their usage, lack of per node or per client secrets, an infinite credential lifetime, and most importantly, a requirement for operator or human insertion. So at HashiCorp, we designed Vault to solve those and many other secret management problems. Vault provides a single source of truth for secrets and credential management in the organization. It provides programmatic access for machines to get their own credentials without a human. And it provides operators or humans to authenticate and get their own credentials. The entire system is encrypted and controlled via fine-grained ACLs and policies that grant users, groups, and machines access to pieces of information stored in the Vault. By being a single source of truth, Vault provides a secrets as a service, allowing machines and humans to authenticate against it using its HTTP API. So let's take a look at Vault's architecture and design outside of the scope of Chef, and then we're going to bring them both together. So here on the screen, I have Vault's architecture. At its core, the only interface to Vault is the HTTP API, and you can see that there on the top. Any and all requests to Vault must flow through that HTTP API. In the middle, we have the barrier. The barrier is the cryptographic seal around the Vault, and all requests must flow through the barrier. The core of Vault is responsible for doing a number of things, including path routing, and everything in Vault is path-based, and those policies and the configurations are based off of those paths. Vault has built-in support for auditing and built-in support for storing tokens and policies and expiring things at the end. Everything in Vault is pluggable, and at the very bottom, you'll see the storage backend, which is the durable storage backend for Vault. So this is read from the top down. If we imagine an imaginary request coming through, it hits the HTTP API, which gets routed to core. Core will then do path routing to a particular backend. That backend is a plugin. It'll do something with that data and return a response, and that gets returned to the client. The backend can also write to the storage mechanism to persist data. And then all along there, the audit broker is responsible for managing all of the different audit logs. Every request and response in the system is logged, and because all requests and responses come through the HTTP API, there aren't any actions in Vault that don't get logged to the audit log, which is a really big checkbox for various compliances. Along the lines of the barrier, one of the key components or key features of Vault is that no one person has complete access of the system. So no one human or no one machine has complete access in the system. The barrier is not just a, if conditional to see if the barrier is opened or the barrier is closed. If you're an engineer, you might be thinking, there's just an if statement that says, if barrier is not equal to open, then reject the HTTP request. And it doesn't work that way. The barrier actually uses something called a Shamir secret sharing algorithm, which I've put up on the screen here. Shamir secret sharing algorithm is a cryptographic algorithm that allows us to decompose a string, or in this case a key, into a number of shares, pieces, such that a subset of those shares can come together to form the original key. So to give you an example, if you were to take a house key, like a physical key that you put into your door, and cut it into 5 pieces, the way Shamir's secret sharing algorithm works is that mathematically, not physically, but mathematically, we would be able to put, let's say, 3 of those pieces back together, and you would still be able to unlock your door. When Vault is bootstrapped and created, that master key is decomposed into key shares or pieces, and you give those to trusted people in the organization. Vault never stores that master key, and the only way to regenerate it is for those keys to come back together. That's important because that's ultimately what forms the barrier. Because that master key encrypts that encryption key, the thing you see furthest to the right, which is ultimately what encrypts the data in Vault. So if a threshold of key shares don't come together to generate the master key, the data in the Vault remains sealed, and thus the barrier remains unpenetrable. And this is why Vault's architecture is so popular, is that it prevents one person from having complete control of the system by utilizing the Shamir secret sharing algorithm. Vault can run in high availability mode, but for the purposes of this webinar, I'm only running a single instance. Excuse me. There are a number of mechanisms for authenticating to Vault. Authentication is the process by which human or machine supplied information is verified against data in Vault or some external service. Some of the authentication mechanisms include username and password, GitHub, LDAP, or more. In Vault, there are 2 kinds of secrets. There are static secrets and dynamic secrets. Dynamic secrets have leases and expire after a short period of time. Static secrets have refresh intervals, but they don't expire unless they're explicitly removed. So the easiest way to think about a static secret is something like encrypted Redis or encrypted memcached. Vault exposes an encrypted key value store such that all data is written, but it's encrypted in transit and at rest. So let's take a look at an example there. Using the Vault CLI, which is just Vault, I can write to secret/foo with any value that I want to. So I can say value equals my secret value, and you'll notice that we get a success message back. I have a Vault server running in the cloud somewhere, and I'm actually making a remote HTTPS call to that API server with the payload, again, encrypted at transit because we're using TLS, and then Vault stored that data in the storage backend at rest. We can pull that data back out using the Vault read command with that same path. Again, everything is path-based. And you'll notice we get back the value as well as a refresh interval. That refresh interval tells us how long the secret should be valid until a consumer should reread it. We can update existing values. So I'll use that same path there. But I'm going to write a value equals new secret and author equals, Seth Vargo. And these values here are just key value pairs. They can be any key value pairs that you would like. And we can read that data back out again, and we'll get back that tabular output of, author equals Seth Vargo, value equals new secret. And we can also list these secrets, and we'll get all of the keys that exist under a particular path. Now, what you might be thinking is this doesn't feel very secure. It wasn't hard. And that's because we've been trained to feel like security should be hard. We have to go through lots of steps and jump through lots of hoops in order to feel secure. But I assure you that in addition to the data itself being secure, it's encrypted at transit with state-of-the-art encryption mechanisms. It's also encrypted at rest with the latest and greatest TLS encryption algorithms. And Vault has been audited a number of times by independent security groups who have verified its security. So even though this doesn't feel secure, it almost feels too easy, that's not because encryption is hard, it's because we've been conditioned to believe it's hard, and Vault makes it easy again. So static secrets in Vault solve some of the problems we listed above, except for per node or per client secrets, this infinite credential lifetime. Remember, things in this generic secret backend are great, but they live forever. So the generic secret backend is great for things like Wi-Fi passwords or things that you don't rotate frequently, but they're not great for things like database passwords or AWS credentials, which you should be rotating on a semi-regular basis. And the secret backend requires that an operator know the secret. I have to actually run Vault write to put the data into Vault. It doesn't generate secrets for me. And that's where the dynamic secrets are really important. Dynamic secrets, or as it's sometimes referred to as the secret acquisition engine, can alleviate those remaining problems. In most cases, Vault can act as the root user for many databases and services to dynamically generate sub-accounts based on a configured policy or role. So let's take a moment to look at AWS as a concrete example. Let's suppose you're a developer who needs access to communicate with the AWS APIs for a project you're working on. The normal process without Vault to get those credentials would be for a human to log into the AWS console or use the AWS CLI tools, create a credential with the proper permissions and attach it an IAM policy to your user, and then somehow securely distribute your credentials to you. And this is problematic because how do we securely distribute them to you? But also the person who created those credentials saw them. They were in plain text. So two human beings actually saw those credentials. With Vault, we can automate the policies and configuration automatically based on a set of rules and configurations. We give Vault a root AWS account or a very privileged AWS account with permissions to create other credentials, and then those credentials map to a series of AWS policies. Once that's configured, developers can programmatically access AWS credentials without human intervention. So we're not sacrificing security. All we're doing is codifying or automating the processes of clicking into the UI or running CLI commands and wrapping it around an HTTP API secured over TLS so that you can automate the process, meaning a human doesn't have to get involved, but the entire process is audited throughout. And let's take a look at what that looks like. I've gone ahead and configured this in advance of the webinar. I've given Vault, the Vault server, an AWS access key and secret key that has permission to manage other users in the system. And I've configured it, and Vault stored all of that data securely. Now what I want to do is I want to assume the role of an individual developer who wants to acquire AWS credentials so I can communicate with the API. And all I have to do is read, which is an HTTP GET request, from the creds endpoint with my particular role, which is developer. And when I read from this endpoint, you'll notice that request took a second. That's because Vault actually went out to Amazon, made an API call to generate an IAM user. And if you're not familiar with Amazon, what I've highlighted here, the access key and the secret key, those are actual access credentials that you could use to authenticate to Amazon's API. You can think of them as a username and password to authenticate to the API. This particular credential has a policy attached to it, a policy that I had uploaded in advance, and that policy just basically gives it permission to create other users. So there's not a lot of policy attached to this. But the important part is that I've codified this entire process. So I can generate more credentials. You'll notice as I run this command, I'm generating new access keys each time I run that command, and that they're valid for 2 minutes. We'll talk about that more in a second, but if you look here, the least duration is 2 minutes, and we'll talk about what that means here in a little bit. Because this process is codified, there's very little room for human error. If I make a typo, for example, I'm going to get an error back saying that role doesn't exist. If I try to access something I don't have permission to, I'll get a 403 saying I'm unauthorized. This path here, the AWS Creds developer, remember everything is path-based, can be controlled with ACLs, and those ACLs can be mapped to authentications in Vault. This allows a Vault administrator or the person who is configuring the Vault to grant authorization based on authentication. Some examples there include anyone in the engineers team of a GitHub organization has access to generate AWS credentials. So anyone in a particular team on a particular organization in GitHub can do particular things in Vault. Or anyone in an OU in an LDAP server can perform certain operations in Vault. And with those techniques, they log into Vault, the humans log into Vault using their LDAP credentials or using their GitHub credentials. Vault verifies their authenticity against the external service provider. You can think of it a lot like OAuth. And then Vault authenticates them and gives them back a token which they can use to authenticate with Vault and perform any requests that they are authorized to do. So you may have noticed that these credentials have a lease duration of 2 minutes. A lease duration on a dynamic secret is the lifetime of that secret, meaning unless that secret is renewed before 2 minutes is up, the credential is going to expire. And when a credential expires, Vault is actually going to go out to AWS and delete that credential. It's going to say this one is no longer valid. So what that means is we put a lifetime on these credentials. These particular AWS credentials are only valid for 2 minutes unless they're renewed within that 2 minutes. I've also put a maximum lifetime on these credentials of 24 hours, meaning you can renew as much as you would like, but the maximum lifetime that you can renew is 24 hours. Meaning the minimum lifetime this credential will be valid is 2 minutes, and the maximum is 24 hours. But if at any point you don't renew for 2 consecutive minutes, the credential will be revoked. In this way, Vault's dynamic secret backend behaves very similar to IP address leases via DHCP. You ask the DHCP server for an IP address, the DHCP server says, here's an IP and a lifetime. After that lifetime hits, you have to tell me you're still using this, or I might assign that IP address to another server. Vault behaves very similarly, and Vault handles the creation and the revocation of those credentials when that lease duration is up. Acquiring AWS credentials is mostly a human-based operation. So let's take a look at generating Postgres credentials, which might be more of a machine-based operation. If you're not familiar, Postgres is a database very similar to MySQL, MariaDB, or MongoDB. And Vault has support for all of those, but I'm just going to be demoing Postgres today. To save time, I've already configured Vault. I gave Vault a very privileged user connection and a connection string to talk to Postgres. And I've created a role in Vault that'll generate a read-only user. So I gave Vault some SQL to run, the same SQL I would run if I was logged into the console, but I've codified it. I've given it to Vault to automate. And now Vault can generate credentials for me. So if I run this Vault read command from the PostgreSQL path, again, everything is path-based, so PostgreSQL is our new namespace. This will go out to the Postgres server that I gave Vault. It will generate a new username and password. This username and password, which I've highlighted here, are real credentials to log into a Postgres database. You can see, again, they're valid for 2 minutes, but this is a real username and password. And I could demo logging into that Postgres database right now. Every time we read from this path, we're going to get a new credential. These credentials are valid for 2 minutes, at which point they must be renewed. And if they're not renewed, they'll be revoked. To renew a secret, we take the lease ID and we just renew that lease ID. And that resets the timer to 2 minutes. Almost all interactions with Vault take place via the HTTP API. And the CLI is actually just a very thin wrapper around that API that provides JSON parsing and table formatting. There's nothing you can do with the CLI that you cannot do via the API. And let me show you an example of that. So the Vault server is actually running on a URL that is vault.hashicorp.rocks. The API lives under the /v1 namespace, and then everything else corresponds to the commands we've been running. So PostgreSQL /creds/read-only. The only difference between using something like curl or a HTTP library versus the Vault CLI is that we have to pass along this header here, xVault token, which is our authentication. It's like our session token to Vault. The Vault CLI caches that for us, so we don't have to worry about it. But since HTTP is stateless, we have to pass this along. So here I'm just asking for another Postgres credential, and I'm going to pipe that to JQ to get some pretty formatted and colored output. So let's take a look at what that looks like. Oh, okay. I messed up. It's okay. This is Vault token. So here we can see I just made a tiny error in that I was using the wrong environment variable, but we get a JSON payload back that I've highlighted here, and you'll notice that payload somewhat matches the data that we saw via the Vault CLI from before. We see the username and the password, the lease duration, lease ID, etc. You'll notice that the CLI did things like added formatting to our lease duration, so instead of 120 seconds, it told us that was 2 minutes, etc. We get some additional information back from the API that we don't see on the CLI as well. So why am I showing you the API? Well, because Vault has a full API, almost any tool which can make HTTP requests is able to communicate with Vault, and that includes Chef. Chef is written in Ruby, and Chef has its own primitives for making HTTP requests. So by combining those resources that are built into core Chef, we can achieve the same behavior that we just did via curl by querying the Vault API directly from Chef. So let's take a look at what that looks like. Let me set syntax. Okay, hopefully that's a little bit easier to read with the color there. Here I have two resources. I have a remote file resource. That remote file resource is basically doing that curl request. So I don't want to back up the file. I'm telling it to hit the vault.hashicorp.rocks/v1/cred/read-only endpoint. I'm passing in that xvault token header, giving it 644 permissions, and I'm telling it to run this Ruby block unless this file already exists. And then that Ruby block parses that JSON for us. So I'm reading that file, parsing the data hash, and then this long line here that I've highlighted is just the YAML file that I've been using, and we're writing that out to database.yaml. So this is a relatively advanced Chef configuration, right? I have a notification, I have a not if block, but basically what this is doing at a very high level is it has one resource which is going to contact the Vault API and write the request to a file. If that file changes, it's going to trigger another resource which parses that file and pulls out the information we need into a format. So you can think of the remote file resource as just the HTTP GET request and the Ruby block as just the formatting call. So let's go ahead and run this. So again, I'm using Chef Client in local mode. And you'll notice that it pulls down the API cookbook. Here is the request that it got back from Vault. It's not pretty formatted, but you can see that that's very similar to the JSON response we got from before, but the username and password is different. It wrote that to temp/database.json, which then triggered the Ruby block to parse that JSON and write out temp/database.yaml. So if we were to cat temp/database.json, you would see we have that data in there. And if I were to cat the YAML file, you can see it did write out that data minus a new line character. So this is great. We just use Chef to programmatically query the Vault API and generate a Postgres credential and store that in a file on disk. But because of Vault's design, each Chef node will receive a different credential. Because remember, each time we query that API, we get a different username and password. So just by Vault's architecture, nodes and applications are getting different credentials, but they have to renew those credentials, meaning at the end of 2 minutes, those credentials that we wrote to a file are going to get revoked unless we renew them. And let's take a look at that renewal lifecycle. So this is what it looks like to renew a credential in Vault. Applications must ask themselves, do they have a secret? If they do have a secret, they have to renew it. If they don't have a secret, they have to request a new one, and then there are success and failure cases through that. And this is a rather complex logic flowchart that we're not going to cover in detail. You can find more on the Vault website, or I'm happy to answer any questions about it later. But what's important is that this is traditionally challenging to implement in an architecture like Chef or Puppet or any configuration management tooling because of their pull-based model, P-U-L-L, meaning they run at an interval. This is an indication that configuration management is not typically the best place to manage this renewal lifecycle. In particular, it would be impossible to have a short-lived secret because they would expire before the tool has a chance to renew them. Fortunately, applications don't have to implement this flow either. There are open source tools which exist to implement that control flow for you, and we call them sidecar applications. HashiCorp makes a number of them. They'll manage that renewal and acquisition workflow and write out a file to disk or set some environment variables. They handle that communication between different processes, providing a common and predictable API to the subsystems. And one of those tools, which I'd like to show you here today, is called Console Template. So here I have a rather complex cookbook, and again, all of this will be available to you afterward. You're free to review these in more detail. This cookbook installs console template into a system service, and then it writes out a template to disk. Console template runs as a service. It handles that renewal. It's going to run as a system process under, in this case, Upstart, and manage the renewal process for us. So Chef is still important in this process. It's responsible for actually configuring and installing the system. But after it runs, console template is actually the thing that's going to go out and acquire secrets and manage their life cycle. Chef is just making sure it's up and running. So I'm going to go ahead and run the Chef client here. You'll notice that this one is a little bit longer. We're writing out a number of configuration files, creating an init file. You could use systemd. I chose to use Upstart because I'm just a little more familiar with it. And you'll notice that if we were to look on this system, there is a console template process running. And that console template process is writing out the database.yaml file. It's in constant communication with Vault. And you can see that because if we take a look at the log file, you can see that the log file from console template is dynamically registering this temp database.yaml file. And if we were to cat database.yaml, you can see that those credentials have again changed. We're running a little bit short on time. I did have an interactive section. If you all were interested, I'll just put the link up here, which is going to be vault.hashicorp.rocks/app. You're all free to join around this. This is the Vault server that we've been interacting with. On here, you can generate a Vault token. So you can click to get a Vault token. It'll generate, this is a real Vault token that'll actually communicate with this Vault server that's running via a Let's Encrypt certificate. And then it gives you a curl command, and that curl command will generate a Postgres credential, which you could use to connect to the database. And you can run that multiple times, and you can see the interactivity. And if you click Get Vault Token again, you'll get a different Vault token. This is actually communicating with the Vault server that we've been using here. And you're free to play around with that. I'll leave it up for a little bit after the webinar, so you can kind of play around with the Vault CLI a little bit. In this webinar, I used Terraform, which is another open source tool by HashiCorp, to provision the Vault cluster. But there are many techniques for deploying Vault, including Chef itself, Nomad, Kubernetes, Cloud Foundry, and Chef's very own Habitat. To talk a little bit more about Habitat and the Vault Habitat creation process, I'm going to turn it over to JJ from Chef. So JJ, go ahead and start your screen share. And while he's getting that running, JJ is going to show us a little bit about how he used Habitat to play around with Vault, learn about Vault, and deploy Vault in some more complex environments as opposed to just a single server. He was able to do some high availability and some joining of other clusters. So we're just waiting a little bit for the screen share to switch on over. And then as soon as that's done, JJ will take it over, and then we'll have a few minutes for questions at the end. So if you do have questions, now would be a good time to drop them in the chat. JJ?
Hey, thank you, Seth. So this is the link. This is my notes, but I'm actually going to be doing this live. So, you know, hopefully the demo gods are going to be smiling upon me. So as Seth was saying, Habitat, in the process of learning Vault, I discovered that Habitat was a great opportunity. So what I'm going to do is I'm going to build up a console backend using Docker containers. And then I'm going to build out Vault, and then we're going to spin it up all locally. So first of all, there are something called core plans inside of Habitat, and we are going to go into the console one first. We're going to do Hab Studio Enter, which if you don't know about Habitat, this is the studio that allows you to build things from the ground up. So I will go ahead and build as if I cannot type. As you can see, I pull down Vault directly into it, then I package it. Console. And then I will be exporting this out as a Docker container because this will be a little bit easier as a Docker container. And I should go ahead and say too, I actually made some configuration changes during this process. As you can see, I go ahead and bind to 00 to all network ports. Now you can actually do this via a runtime change for the supervisor, but for simplicity's sake, I went ahead and changed the actual configuration. So as you can see here, I'm building the Docker container, and then I'm going to, as soon as this is done, I'm going to drop out of the studio, then go back into Vault. And then, as you see, there's a client.sh here. But before we do this, I am going to spin up 3 instances of console here, so we can actually get our console backend up and running. As you can see, I was testing this beforehand because, you know, got to do that. As you can see, this is the console agent running. I'm listening to all these addresses. As you can see, these are the cluster addresses. So what I'm going to do is I am going to go into another Docker container here and actually going to get all of them to talk to one another. Console. And as you can see, successfully joined the cluster for 3 nodes. And as you can see here, there they are. They are now talking to one another, which is pretty cool, you have to admit. And then if you turn around, I can go into the vault here. So I can go to add to the enter. And I can do build, which will pull down the newest version of Vault, which is, last time I checked, 6.6.2. And I will export this also out as a Docker container. And as soon as this is done. Now, you're probably wondering why I'm doing this. Well, it's mainly because you can actually now play with, in a closer to production-like setting with a console backend and Vault frontend all locally here. As you'll see, I'm actually doing this live, and there will be, you can actually play locally and actually see how it all comes together, which is pretty slick, isn't it? So, I went ahead and did this. So I will go ahead and drop out of this here in a moment. And I will spin up as soon as this is done. Building the Docker container. Thinking about it. There we go. So I will go ahead and drop out of this, and I will spin up the Docker container here. And as you can see, I have a cluster address where I have the backend of console, so it is actually talking to our console backend. So if I come over to this guy right here, and I go ahead and refresh, I have the web GUI up, including the vault where I can see this is sealed. So we're going to need to go ahead and unseal this. And let us go ahead and export this. And so I can go to vault. If this is right, did I get it? Did I get it? Did I not? Oh, it's 7. Oops. That was my mistake. As you can see, I even have a little note there to tell me to do whatever the IP is. And there we go. As you can see, as Seth was saying a moment ago, here are the unsealed keys inside of that, so I can actually build it up. So I can actually do .vault unseal, and I can take this key. I can do it again, and then I can do this. Vault. Oops. Vault unseal. And as you can see now, it is unsealed. And if I come over here and I refresh, I can go into services, and as you can see, it is unsealed. So once again, this is just kind of a quick little example and a quick little easy show of how to set up a relatively production-like system with Vault and Console. There is a dev mode with Vault and also a dev mode with Console. But if you're trying to learn how to get the more advanced setup, this is a way to leverage Habitat to build the containers and run it locally and get it going. Thanks so much.
Awesome. Thank you so much, JJ and Seth. We do have a few minutes left for Q&A, and we've got some great questions from the audience. So let's go ahead and dive right into those. Our first question is, does the Vault command have to take place in the context of some existing Chef server user?
No. So all of the interactions with Vault take place over the API. So there's no specific user or UID that you would need to run with Chef. The only thing to take into consideration is if you are writing out any files or any sensitive information, you'll want to make sure that those are owned by the proper user on the system and have permissions, because you are writing sensitive or secret data to the system. You don't want to accidentally leak those to other users on the system.
Okay, thank you. Our next question is regarding generating AWS credentials for developers via Vault. Is it possible to generate or store multiple static developer credentials behind the same AWS Creds backend so that each developer only has access to their own set of credentials? For example, Joe has access to AWS Creds Joe, but not AWS Creds Mary. And Mary has access to AWS Creds Mary, but not AWS Creds Joe.
Yeah, so that's a really great question. I think my screen share is back up. Is it?
Yep,
you all see that?
Got it.
Okay, perfect. So everything in Vault is role-based. So it is totally possible to achieve the exact thing that this particular user asked. But generally, we think about things as roles. So instead of having, Joe and Mary and Alice being their own individual users, which is totally valid, you can totally do that, we think about things as roles. So generally, you would think, okay, Joe and Mary are developers, and Alice is a designer maybe. So you would have a developer role and a designer role. I configured this in advance for sake of time, but I'm just going to go ahead and show you very quickly. To generate a role, we write to roles and then the name of the role. So whatever name I put here is the name of the role. So in your example, we'll use Mary. And then I have to give Vault the policy that I want it to use to create this user. And this is an IAM policy. So by putting the dash there, Vault's going to read from standard in. So I'm just going to go ahead and copy and paste something. This IAM policy here is going to give EC2 access across the board. So this will give Mary or anyone who has permission to read from the role Mary full access on the EC2 platform. And then I'll hit Control D here, and you'll see that wrote the role. So I now have two roles. I have the developer role and I have the Mary role. And if I were to read from AWS Creds and then the name, which is Mary, we'll get back credentials. And you'll notice there's no differentiator here. They're the same access key and secret key, syntax and look and feel as before, but this one is tied to a policy that gives EC2 permissions where the other one did not. And then I can revoke these credentials, which I'm going to do using this lease ID. So I'll go ahead and revoke those credentials, and Vault went out and early, before the 2 minutes, deleted those from EC2 so that even if you tried those credentials right now, they would be invalid.
Perfect. Thanks, Seth. Does Vault need a plugin to work with databases? Could it work with a Microsoft SQL database with .NET? For example, PostgreSQL, what if a user has a query running that runs past the expiration of its credentials? Will Vault revoke the creds during the running query, and will that break the query? Would Vault or PostgreSQL notice the situation and wait until the query is done to revoke the creds?
Yeah, so those are both great questions. The first question in terms of does it work with databases, Vault has a number of secret backends, which I'm showing here on my screen. They're listed on the website, vaultproject.io. AWS and PostgreSQL are some of the ones we saw today. MS SQL, which is Microsoft SQL, MySQL, which is compatible with MariaDB, MongoDB. There are a number of secret backends, and it is possible to write your own. It's very easy to write your own secret backend. There are a number of advanced techniques which we just didn't have time to cover in the webinar today, including Vault can act as a certificate authority, so it can do TLS and PKI. It can replace SSH or integrate with SSH so that you don't have to distribute key pairs or usernames and passwords. And the list is always growing. Some of these are contributed directly by HashiCorp. Some of them are contributed by community members who have a need for them. So it does integrate with Microsoft SQL database. Whether it integrates with .NET, I don't know, but let's see, a quick Google search. So HashiCorp Vault, .NET library, let's see what comes up here. And it does look like there is a library here, a .NET library for integrating with Vault. So I can't comment on the the stability or the quality of that, but there is a library, and there is a section on Vault's documentation for libraries that we have vetted. So some of the open source libraries here, oh look, that is one, the C# Vault Chart library that we have vetted. In terms of the question about what happens if the query is running, Vault will make a best attempt. So off the top of my head, I don't know the exact series of commands, but it'll attempt a disconnect, which will tell the database itself to actually stop doing what it's doing. It'll wait a period of time before it'll force disconnect. And then when that doesn't work, it eventually takes the equivalent of kill-9. So very similar to how like Unix would stop a process. It would try to get it to gracefully stop. It would give it some time to clean up, and then if it hasn't been done by then, it would force kill it. That's very similar to how Vault works. So it's really a context-based thing. For things that are long-running, like if you have a very long-running query that takes 6 hours or a batch job or something, there are other options. You can do periodic tokens, which don't expire. Or periodic credentials which don't expire. There are some advanced techniques for those types of jobs that do have long-running processes.
Super, thank you. Will you store the unsealed token in a Chef databag and run the unsealed before you run the Postgres cred retrieval? If not, would you just leave the vault unsealed?
So this is a good question. I think there's a little bit of confusion because there's two types of tokens. So the unsealed token, which JJ talked about, was that piece of that Shamir secret sharing algorithm. That has no privilege in Vault. That's just to generate the master key to unseal the Vault. It can't be used to make any other requests in Vault. The Vault token is like your session token. When you log into a website, you put in your username and password, and then your browser gets a cookie back. And it stores some data in that cookie, and some of that data is a session ID. That's what a Vault token is. It's your session ID throughout the system. So the question is, how do you get that initial Vault token onto the system so that you can make that request? Which is a very good question. It's a very common question. It's how do I get that first secret onto a system? And there are a few techniques. The first technique is to use an encrypted data bag. You would have some other process, maybe the Chef server or some bootstrapping process, generate the Vault token, put it in the encrypted data bag. Then at bootstrap time, knife bootstrap or whatever, the node would pull down that encrypted data bag, pull out the Vault token, and make a request. The downside to that approach is that then a human or that other machine knew what that credential was at some point. We do have some of advanced features in Vault, such as cubbyhole response wrapping, and other authentication backends, which I see actually the next question is related to that, which I'll just read it now because I think I'm going to answer them both at the same time. The next question on the list is, what is the Chef to Vault authentication configuration best practice? We have different authentication backends. If you're in AWS, we've worked with them to make a really great authentication backend where you can authenticate directly in EC2. There's a ton of documentation on it, but effectively using some well-known information, we can authenticate you directly against EC2. We don't yet have an integration with the Chef server. That's something that we're very interested in, where the Chef server would be able to do the authentication. But Vault basically needs to make an API call to something with pieces of information, and that API call needs to come back with like a yes or a no. We do have things like cubbyhole, which allow you to have like very short-lived tokens and wrapped tokens that allow you to securely distribute that first secret on a very short lease, such that the area, the surface area, is very limited. But this is a relatively, how can I say this? It's not an unsolved problem, but it's solved differently depending on your environment. So it's challenging to answer, a very broad question of how I would do it without knowing more about the information. If I was on AWS, I would definitely take a look at the EC2 authentication backend. If not, the app role and app ID backends are really great, as well as cubbyhole.
Perfect. Thank you so much, Seth. We are nearing our time limit here, and we still have several questions that have gone unanswered. So I just want to let everyone know that if you've submitted a question that we haven't got to yet, we will follow up with you directly via email after the live session. And in the next week or so, we'll publish a blog post on the Chef blog to recap this presentation and all the additional Q&A. Any closing words from Seth or JJ before we go?
No, just a reminder that the commands and kind of the script and everything I ran here today will be open source. Chef will send out a link to that repo. It'll be open source on GitHub here very shortly. So if you missed something or if you want to go back and review it, it'll be open on GitHub. And if you have any questions that we don't get to here, please ask and we'll follow up.
Excellent. Thank you so much. And thanks also to our audience for taking time to join us. Before you go, please take a moment to rate this presentation and leave your feedback in the Rate This tab of your viewer screen. I think that's it for today. Thank you again for your time and have a wonderful day.